students, welcome to the series of lectures on differential geometry. This is the first video of the series. Here we shall see some basic ideas regarding differential geometry. Differential geometry, an introduction. To study the concept of differential geometry, one should be familiar with differential calculus, integral calculus, linear algebra, and multilinear algebra, because differential geometry uses all these concepts as its fundamental. Okay, when you hear the word geometry, the first person comes in mind is Euclid. And we all know he is the father of geometry. Considering the geometry in 3 dimensions and measuring its parameters like a position from coordinate axis, for instance, you might have given an example by assuming the corner of the room as origin, right? Or you may consider a 2-dimensional Cartesian system. All these are considered to be Euclidean geometry. As we have learned right from our school, geometry means measurements, right? There will be some units, say centimeter or meter or millimeter, that acts as a building block. Any parameter should be expressed in terms of some multiple of this unit, right? Like 5 centimeter, 6 centimeter, 4 meter, like this. This is one perspective. Now let me give you an example. Suppose you want to go to a shop to buy some groceries. There you notice 2 queues. If you want to get the things done faster, you obviously choose the shorter queue, right? Now let me check which queue is short. This queue has 1, 2, 3, 4 units, right? And this 1, 2, 3, 4, 5, 6, 7. So it is obvious to choose this queue, right? But think for a moment. If the people are standing in this fashion in the first queue and in this fashion in the second queue, now which one do you choose? This one, right? The second one. What made you to choose the second queue? That is the number of persons. And the measurement has nothing to do with this. This gave rise to another notion of treating geometry by considering the concept of point as a building block. Here, if there is a line, then it is viewed as the collection of points. This idea is mainly used in non-Euclidean geometry. The 2 concepts that are very important in this notion, points and their mappings. If you are more curious to know about this, do search this thing, a coffee mug and a donut. These 2 are equivalent. If you consider the notion of measurements, then you cannot land at the desired result. I don't go much into the theory of this right now, but do search the thing. I can give some hint. See, here it is. Donut is equivalent to coffee mug, right? And these are one-dimensional stuffs that are equivalent. And for 2 dimension, this is an example. Okay, first of all, we shall understand what does a curve mean. If I ask you to give example of a curve, you may say a circle, a parabola, a straight line, right? But how to define it? For that, there are mainly 2 ways. Defining it as a level curve or as a parameterized curve. Now we shall understand the meaning of level curve. See, this circle, line, and parabola can be expressed as x square plus y square is equal to 1, the unit circle, x plus y is equal to 1, the straight line, y minus x square is equal to 0, this parabola. Observe here, the LHS here is a function of x and y, and the RHS is a constant. Thus, it is in the form of f of xy is equal to c, where f of xy is a function of x and y, and c is a constant. So, collection of all such points that satisfy this equation is called a curve. In 3 dimensions, it can be expressed as this, f of x, y, z, where f is a function of x, y, and z, and c is a constant. In general, a curve in R3 is defined by a pair of equations as f1 of x, y, z is equal to c1 and f2 of x, y, z is equal to c2. Let me make you visualize this. See, consider this example. Right. Here, let me take a plane. See this plane, z is equal to c. This is parallel to xy plane, right? So where c is a constant, observe here, this plane cuts this surface. So this is the intersection path. There you can see the one in black color. For this we call a level curve, because this curve is obtained when this parallel plane is at level C. If I change the value of C, see this curve also changes. In general, a curve can be defined as the intersection of two surfaces like this. Here you can see a curve. In general, a curve is described as a path traced by a moving point. See, like this. Now we shall see what is meant by parameterized curve. So parameterized curve is a mapping alpha from the open interval a comma b to Rn for some ab with minus infinity less than or equal to a less than b less than or equal to infinity, where ab is an open interval and it is given by like this. T is a parameter. In general, parameterized curve is represented as alpha of t is equal to alpha 1 of t, alpha 2 of t, and so on up to alpha n of t, where alpha 1, alpha 2, and alpha n are the real valued functions of t. Right. So parameterized curve is a mapping from an open interval to R2. Here it is an example of R2. Similarly, in R3, it is a mapping from open interval to R3. We shall see it more precisely. Let this be an open interval and t takes values from this interval. First, let me consider a curve in R2. Here, f of t and g of t are some real valued functions of t. And the mapping A from this interval to R2 is a parameterized form of the curve. So this is the curve. Observe the mapping here. This red dot, it gives the image of each point in the interval, right? Similarly, we can consider it in 3 dimensions. See the mapping B. The green dot here represents the image of each point of the interval. Okay. Here is an activity. Give the general form of the following: circle, parabola, ellipse, cylinder, sphere, and plane. Hope you will do that. Okay, I'll stop the video here. We shall continue this in the next video. Thank you.